So now we're going to take a look at some trig identities that we can prove using some algebra techniques. So this first one we're going to look at is the identity 6 cosecant squared theta minus 7 cosecant theta minus 3 divided by 1 plus 3 cosecant theta equals 2 cosecant theta minus 3. So this one is kind of unique in that we're not going to use any trig identities. We're only going to use algebra techniques. So notice that the only trig expression we have in this whole identity is cosecant theta. So if we were to replace cosecant theta with something that looks a little bit more familiar from algebra class, say x, this would be the same as 6x squared minus 7x minus 3 divided by 1 plus 3x equals 2x minus 3. Okay, so this is really just a rational expression that we're simplifying. Okay, and this is true as long as our denominator is non-zero, because we can factor our numerator to be 3x plus 1 times 2x minus 3. And then we have a 3x plus 1 over 1 plus 3x. That would cancel. And we'd be left with 2x minus 3. And we would factor our numerator using your factoring technique of choice, using the AC method, using slide and divide, using trial and error, whatever your favorite method is for factoring quadratics. So we're going to apply the same approach to our trig expression. So what we're going to do is rewrite our numerator by factoring as 3 cosecant theta plus 1 over 2 cosecant theta minus 3. Okay, and if we FOIL this out just to check, we're going to have 3 times 2 is 6 times cosecant squared theta minus 9 cosecant theta plus 2 cosecant theta is the negative 7 cosecant theta, and then 1 times negative 3 is negative 3. So that is indeed correct. Okay, so now we have 3 cosecant theta plus 1 over 1 plus 3 cosecant theta. That will cancel, and we'd be left with 2 cosecant theta minus 3. Okay, and that's exactly what we were to set out to prove, that the left-hand side equals the right-hand side. So often using factoring, this is one way to do it, to simplify what looks like a rational expression, or using factoring, say canceling out, or factoring out rather a greatest common factor from an expression is another way to move forward when we're proving trig identities. Okay, so next let's take a look at some trig identities that have some fractions, and we'll look at some ways we can handle those. Okay, so we're going to take a look at the identity 1 plus 2 secant theta over secant theta equals 2 plus cosine theta. Okay, and again, we're going to start with the left-hand side. We're going to simplify it to prove that it equals the right-hand side. Now, one method we can use if we have a sum or difference in our numerator, particularly if we have just one term in the denominator, so note that our denominator doesn't have a sum or difference, it's just secant theta, is to break up fractions. So we can use the fact that a plus b over c is a over c plus b over c, or if there's a difference in the numerator, a minus b over c is a over c minus b over c. Okay, and sometimes that's helpful. For example, in this case, if we break our fraction up on the left-hand side, our left-hand side will be 1 over secant theta plus 2 secant theta over secant theta. Okay, and now we can do some simplification. We have secant theta over secant theta, which is 2, and 1 over secant theta, using a reciprocal identity, is cosine theta. So this is cosine theta plus 2, which is the same thing indeed as 2 plus cosine theta. Okay, so indeed we've shown that the left-hand side equals the right-hand side. Okay, so to recap, whenever you have just one term in the denominator and a sum or difference in the numerator, it's often beneficial to break fractions up. Now sometimes it's going to be beneficial to do the opposite of that. So sometimes we're going to have a sum or difference of fractions, and those fractions have different denominators, and sometimes it's beneficial to add or subtract those fractions and turn them into one single fraction and then simplify. Okay, so let's go ahead and do an example like that. Okay, so let's take a look at the identity secant of beta over sine of beta minus sine beta over secant beta equals tangent squared beta plus cosine squared beta over tangent of beta. Okay, so again, we're going to start with the left-hand side and show that it equals the right-hand side. Okay, so how are we going to do that to start? Well, we have two fractions that have different denominators. So in order to subtract them, we need to put them under common denominators. So we have secant beta over sine beta, okay, minus sine beta over secant beta. So in this case, our denominators are sine beta and secant beta. So our common denominator would be sine beta times secant beta. We'll take our first term and multiply the top and bottom by secant of beta. Take the second term and multiply the top and bottom by sine beta. Okay, so then we end up with a single fraction, because our denominators are the same here. Single fraction will be over the denominator sine beta times secant beta. Now we subtract our numerators and we get secant squared beta minus sine squared beta. Okay, so I did skip an intermediate step here. Notice that our first term is secant squared beta over sine beta secant beta. Our second term is sine squared beta over sine beta secant beta, so we can subtract those fractions because now we have a common denominator. Okay, so we have something that looks similar but not quite like the term on the right-hand side. So we want to make what we have here look like tangent squared plus cosine squared over tangent. So now we want to fall back on some of the techniques that we talked about in the last lecture. So note first, we have a sine times a secant. We can simplify this by using a reciprocal identity. Secant is 1 over cosine. So this is sine times 1 over cosine. And now we can use a quotient identity and write our sine over cosine as tangent. Okay, so we get that our denominator simplifies to tangent of beta. Okay, so that was the easy one, because generally if we're multiplying trig expressions and we don't know how to proceed, changing things to sines and cosines and then going from there is a good way to proceed. And then always keep in mind that we do have an end goal in sight. We want to turn that denominator into tangent so we know where we're going. Okay, now we look at the numerator. And we have a secant squared and a sine squared. We want to turn that into a tangent squared and a cosine squared. So whenever we're trying to change trig functions squared, you always want to think Pythagorean identities. And we can use the fact that secant squared of beta is 1 plus tangent squared beta. So that's our Pythagorean identity, 1 plus tangent squared is secant squared. And sine squared is 1 minus cosine squared. If we take sine squared beta plus cosine squared beta equals 1 and solve for sine squared. So using our Pythagorean identities and rewriting, we can write our numerator as 1 plus tangent squared beta plus 1, minus, I should say. So we still have a minus sign, so let's revisit that. So we're subtracting, so we're going to subtract 1 minus cosine squared beta. So here we have 1 minus 1, that cancels. And we're left with tangent squared beta minus, so we carry the minus sign through, so it's minus is plus cosine squared beta over tangent beta. Okay, and that's exactly what we set out to prove. And so here we're subtracting two fractions, so we combine them using common denominators, rewrote the denominator using a quotient identity, and then rewrote the numerator using Pythagorean identities. And then we'll look at one last algebraic technique that's helpful whenever we have a sum or difference in a denominator of a fraction. Okay, because if you have a sum or difference in the denominator, we can't break up fractions like we did 2 examples ago. So if you have a sum or difference in the numerator, then you can break that up into a sum or difference of fractions. But it's not the case that if you have something that looks like a over b plus c, that's not the same as a over b plus a over c. Okay, so we can't just do that breaking up of fractions if we have a sum or difference in the denominator. Okay, so instead, what we'll do is look at the so-called conjugate. And you've seen the idea of the conjugate before when you were rationalizing denominators and doing complex conjugates. So recall that algebraically, the conjugate of a plus b is a minus b, and the conjugate of a minus b is a plus b. Okay, so for example, if we wanted to simplify the expression tangent of t over secant of t plus 1, and we wanted to show this equals secant of t minus 1 over tangent of t. All right, so once again, we're going to start with the left-hand side, tan t over secant t plus 1, and try to manipulate that and show that it equals the right-hand side. Okay, so here we don't have a sum up top where we can break the fraction up. We have a sum in the denominator. So what we'll do to try to simplify this is multiply the top and bottom by the conjugate of the denominator. So we're going to multiply the top and bottom by the conjugate of the denominator. So this is something we can always try if we have a sum or difference in our denominator. So the conjugate of our denominator will be secant of t minus 1. We just change that plus sign to a minus sign. Okay, so that's going to end up being tangent of t times secant of t minus 1 over, now if we FOIL out the denominator, we're going to have secant t plus 1 times secant t minus 1. This is the difference of squares factorization. So that's going to become secant squared of t minus 1. Now this is one of the reasons why this multiplying by conjugates works in a lot of cases. So notice what we have now is something involving secant squared t. Whenever you have a trig function squared, you want to think Pythagorean identity. And if we use Pythagorean identity, secant squared minus 1 is tangent squared. So we can rewrite that denominator as tangent squared of t, and note that we have a tangent of t up top, a tangent of t on the bottom. So now we're doing our factoring and canceling out common factors, and that leaves us with secant t minus 1 up top and tangent of t on the bottom, okay, which is exactly what we set out to prove. Okay, so here are some methods for simplifying some more complicated trig identities where we're not just using our fundamental identities, we're using them in conjunction with some algebraic techniques.